You know, when you look out at a lake, you see the sun sparkling on the surface. But right under that glimmer, there's this incredible drama unfolding. A single beam of light travels 93 million miles, plunges into the water, and kicks off this whole chain reaction that basically dictates all life below. In this explainer, we're going to follow that journey. We're going to see how this fundamental dance between light and water becomes the very engine for our aquatic ecosystems.
So here's our game plan. We're going to follow a single photon of light on its incredible trip. First, we have to set the stage, talk about the unique properties of water itself. Then we'll get to know our main character, the photon. We'll see its big moment at the water's surface, follow its really tough journey down into the depths, and then finally, we'll understand its ultimate life-giving role. Let's dive in.
All right, first up, let's talk about the stage for our whole story, water. I mean, before we can even begin to understand how light acts in the water, we really have to appreciate what makes water so darn special in the first place. Its molecular properties, well, they're the reason life as we know it is even possible.
Okay, the whole secret to water's power? It's all in its shape. It's what we call a polar molecule, which means it basically acts like a tiny magnet. You've got the oxygen end, which is a little negative, and the hydrogen ends, which are a little positive. This simple polarity is like the master key that unlocks almost everything else, starting with its amazing ability to dissolve nutrients and make them available for life.
That unique structure also controls water's density. Now, pure water is our baseline, right? 1 gram per milliliter. But that number changes as soon as you start dissolving stuff in it. And believe me, this isn't just a boring number. It's a huge driver for the entire ecosystem. These tiny differences in density are the very reason lakes form layers, or stratify, creating completely separate worlds and habitats all within the same lake. And here we go, one of water's superpowers, its ridiculously high specific heat capacity. Just look at this chart. Water can soak up a massive amount of heat from the sun without its own temperature going crazy, totally unlike air or a chunk of iron. This property means lakes and oceans act like these giant thermal batteries for the planet, creating super stable environments where life can just thrive without these wild daily temperature swings.
Okay, so we've set the stage with water. Now let's bring in our main character, light. What exactly is this energy? This stuff that travels 93 million miles from the sun just to power our planet's lakes and oceans.
So, the light we see is actually just this tiny, colorful slice of a much bigger thing called the electromagnetic spectrum. The colors our eyes can pick up, all the reds, greens, and blues, they exist in this really narrow band, from about 400 to 700 nanometers. And that's no accident. Life on Earth has evolved to perfectly tap into this specific window of energy. It's like the Goldilocks zone of the spectrum, just right for seeing and for photosynthesis. This brings us to a really fundamental, almost philosophical question in physics, and it's super important for what comes next. When that sunbeam hits the water, what is it really? Is it this continuous wave, kind of like a ripple in a pond, or is it more like a hailstorm of tiny individual particles?
Well, the truly mind-bending answer from quantum mechanics is, it's both. It's wild, right? Light travels through space as a wave, which is defined by its color, or wavelength. But the second it hits something, the moment it smacks into a chlorophyll molecule, it acts like a particle. It delivers its energy in this little concentrated packet called a photon. So we have to keep both ideas in our head. It travels like a wave, but it hits like a particle.
Okay, so our photon has finished its long journey, and now it's right there at the water's surface. This first meeting is the moment of truth. In just a fraction of a second, its entire fate is about to be decided.
So right at this boundary between the air and the water, 3 things can happen. Some of the light is going to be reflected, just bouncing right off the surface like a mirror. Some of it will be transmitted. It'll successfully make it across the border and start its underwater journey. And as it gets transmitted, it also gets refracted, which means its path literally bends as it enters the denser water.
Now, even though we notice that glare on the water, the amount of light that actually gets reflected is pretty small when the sun is high in the sky. Most of it gets in. Reflection only really becomes a big deal when the sun is low on the horizon, like at sunrise or sunset. That's when the light hits the water at a really shallow angle, and you get that intense, blinding glare all the way across the surface.
So our photon made it. It got past the surface, it was transmitted. But its journey is far from over. As it starts traveling down into the water, it immediately begins to get weaker and weaker. This process is called attenuation.
Now, this fading, or attenuation, happens because of two things. First is absorption. This is where the photon's energy is just completely captured. It gets turned into either heat or into chemical energy through photosynthesis. The second thing is scattering. Here, the photon doesn't get absorbed, but it bumps into a particle or a molecule and gets sent flying off in a totally new direction, kind of like a pinball. Both of these things work together to make the light disappear as you go deeper.
And check this out. This is where that particle nature of light is so important. A single, high-energy photon can actually carry enough punch to shatter chemical bonds. It's a process called photolysis. This is a super important natural cleanup service in lakes and oceans, because sunlight is constantly breaking down pollutants and other complex stuff into simpler, harmless forms.
Now this is absolutely crucial. Not all light fades away at the same rate, and this table shows you why. The longer wavelengths, like red light, they get absorbed super fast. They're pretty much gone within the first few meters. But the shorter wavelengths, especially blue light, they're much tougher to absorb, so they can penetrate way, way deeper. And this is exactly why deep, clear water looks blue. It's literally the only color of light left down there.
Okay, so we've covered a lot of the physics of how light moves through water. But so what? Why does any of this matter? Well, it matters because these physical rules create the biological reality for every single living thing under the surface. Light is the fuel for the entire aquatic engine.
So what's the end result of all this physics? Light is basically the master architect of the underwater world. Its energy fuels photosynthesis, which builds the entire food web from the ground up. Its heat creates those thermal layers we talked about, structuring the physical habitat. Its presence allows for vision, which drives all the predator and prey behavior. And ultimately, just how deep that light can go, well, that determines the literal boundaries of where life can even exist.
Because of this, the light gradient splits the lake into two totally different worlds. Up top, you have the photic zone. That's the sunlit, productive part that's just bustling with life. But below it, you have the endless twilight of the aphotic zone. This is a world where photosynthesis is completely impossible, and survival depends entirely on the slow rain of leftover bits and pieces from that vibrant world up above.
And that's our photons journey. What a trip, huh? Let's do a really quick recap of the most important things we learned in this explainer. First, we saw that water itself, being a polar molecule with a high specific heat, is this uniquely stable place for life to even get started. Second, we learned about light's weird dual nature, how it's both a wave and a particle. And when it hits the surface, a little bit bounces off, but most of it enters and gets bent or refracted. And third, we followed the light as it got weaker with depth, getting absorbed and scattered all along the way. And we saw that red light vanishes first, while blue light makes it the deepest, which is what colors the underwater world. So the next time you're standing by a lake, I really hope you see more than just a sparkly surface. I hope you see the journey, the physics, and the incredible life that it all creates. And to really lock this in, go ahead and test yourself with these questions. The answers hold the key to that hidden engine that powers our planet's blue spaces. Thanks for joining me on this explainer.